And I think we'll probably start from this slide here, though we've already covered this one. Maybe not. Let me see. Start from this one and we'll go from there. Okay. Get my pen set up. Now, before we get going, let me go over just a couple of, I imagine they're fairly minor announcements as far as this class is concerned. First, I have a question for you. Are any of you in a first mini-term course? You are? Okay. Did you know they finally opened the student course evaluations for it? Huh? Yeah, fantastic. Okay. They didn't open them, what, till last night or sometime like that? That's what one of my students told me this morning. That's the first I saw of it was last night. So, anyway, they have been open. So if you are in a first mini, or if you know of someone in a first mini-term course, please tell them those are open now because they were very late in opening them. And if you don't check your email frequently, you may miss and not get those done. Okay, so that's one. Next, there's a few more things. We are getting near the end of the first mini-term. That will be next Tuesday or Wednesday will be the end of the first mini-term, meaning second mini-term will be starting Thursday, okay, of next week, 1 week from tomorrow. Remind me of your name? Savannah, got it. Okay. All right, good deal. Now, why is that important? This class is in really good shape, by and large. I think of all the people who are coming or still may be coming, all but 1, 2, 3 have turned in the first test. Okay? Now, why do I say that? Well, shortly after first mini-term is over, we're at midterm. And sometime shortly after midterm, they usually open up what they call midterm progress reports. And in that, I have to report anyone who has a D or an F at midterm. Well, if I have no work from you, or if you have a D or F at midterm, then I need to report that. It doesn't hurt you in any way, but it may get people, contacting you and saying, is there anything you need for tutoring or other things like this. So if you don't want the hassle, please get your work in. Like I said, there's only 3 of you, and I think I'm preaching to the choir. The ones who are here, I think, have pretty much turned in their stuff. It's ones that are not here that have not yet turned in the first test. But you still have your second test out, too, and for those who didn't do quite as well in the first test, you can still pull that up on the second test. So try to get the second test in as soon as you can as well. And that way, I'll have a grade, so I won't have to put down D or F at midterm. So try to get those in sooner rather than later. All right. The other announcements are a bit more personal in nature, just because a few modifications to my schedule, not permanent, just temporary. First, I think I may have told you last week that I had to go to meetings with the state on curriculum development last Friday, so I was out Friday, was not in the office at all on Friday. I was here at 6 o'clock in the morning, we left, and we got back around 3:30 in the afternoon, making for about a 9.5-hour day when technically I'm only supposed to be working 4 hours on Fridays. Okay, so more than twice. So I asked my boss if I could have this Friday off. He said yes. I'm almost regretting it now because I've got so much work to do. I need Friday to be working on it, but we've got plans. We're going to be out of town, so not going to be on campus Friday at all. Birmingham West Campus, 8 to 12, not going to be there. Okay, and that leads into a week that's so bizarre. Tuesday, I can't remember if I told you all this or not, but I have a mild form of leukemia, and so I have to see my hematologist 2 or 3 times a year, and it just happens to be Tuesday is when it is. he only sees patients on Tuesday mornings. If I could see him on a Friday afternoon, that's when I'd schedule it. He doesn't see patients on Friday afternoon, only on Tuesday mornings. So I've got to be off campus Tuesday morning from about 9 until around 12 or so. So most of the time I don't have many office hours on Tuesdays in those time frames. So it's only my classes that meet then that will be a big issue. And it is a big issue, okay? But for this one, you probably wouldn't be coming by then anyway. But if you were, don't. Between 9 and 12, don't bother. I'll be at the Kirkland Clinic or Whitaker Clinic or somewhere. Kirkland Clinic, okay. So that's Tuesday. Thursday of next week, why does all this happen in the same week? I have a meeting in Tuscaloosa that I have to be at. Now, it's sort of personal, but it also is sort of professional in that because I'm retiring next year, they want you to go to a retirement seminar. It lasts all day long, and I told them what town I want to go to because they don't offer any in Birmingham, biggest city in the state. They don't offer any in Bessemer, which, you know, is not that big, but I would hope. Nope. Tuscaloosa was the closest to Bessemer, so that's where I chose. They assigned me the day, and they assigned me Thursday. Okay. I wish they did Fridays, but they don't do any on Fridays. That would be too convenient for us, less convenient for them. So no, so I will be off campus all day on Thursday of next week. Okay. I say that, but if the meeting gets over in time in Tuscaloosa and I'm driving back home by Bessemer, it's not yet 6 o'clock, I will go into the office and get some work done before 6 and then drive on home from there. But if they last too late in Tuscaloosa, I'm all the way home. Then, finally, on Friday of next week, I have another appointment. This time it's a dermatology appointment, but this one I asked them to schedule me in the afternoon. I'm pretty sure they did, but I don't remember what time. So if it's any time after, say, 12:45 or 1 o'clock, I won't miss any office hours that day. But if it's like 12:30, I'll probably have to leave just a little early in order to get to the appointment on time. So that's the week. It's going to be crazy. Mostly office hour problems, but taken care of. Next, any questions on anything we've covered so far? Anything like that? All right, we left off, and I actually have 2 marks on the page, and now I'm beginning to wonder which one. Are we down at Blaise Pascal? Are we up on page 316 at the top of the page? I think we did the top of the page, didn't we? Okay, yeah. Yeah, if you got it, I'll take it anytime you're through with it, whether today or next week or whatever, okay? Is that the first or second one? Second, okay, yeah, I'll take it anytime. There's still 3 or 4 people who haven't turned in the first, but like I said, I imagine they are the people who are not here, not the people who are. Get your name, please. Second? Okay. Alyssa. Good deal. Okay. So anytime you want to turn in any test, you can. I'll take them anytime. Good deal. Thank you. Ooh, here they go.
Is that okay?
Oh, that's
fine. It has
fine.
all my name on,
Yeah,
on everything.
that's all right.
Okay.
I'll try to keep them together.
Okay.
Thank you. Okay. More the merrier. Yes, I love grading. Yes. Okay. Thank you. All right. Now, good deal. So, did anyone have a book open to remind me?
We stopped at stress.
Huh?
We stopped at stress.
At stress. Okay, did I give you the formula? S equal F over A.
Yes.
Okay, that's where I thought it was. I'm going to get rid of these 2 marks on the same page so I won't get you confused. Okay, so let's start there. Since that's the last thing we said. Stress is defined as the applied force applied over the given area. Okay. Now, I realized that what came before this, to me, was pretty boring. Okay. We went through lots of different terms that dealt with properties of solids. And if you flip back a couple of pages, you'll see tensile strength, force required to break a rod divided by the cross-sectional area, force per unit area. That's the stress, okay? The bottom of the page, the hardness was similar. It was mass per unit area. Not quite the same, but similar, okay? And then here with the springs, we had stress as applied forces per unit area. Now, this stress is often called a variety of things. It is, of course, stress. In other contexts, it will actually be called pressure. Okay? And if you think about it, stress and pressure, even in everyday language, not too different from each other. Pressure is usually measured, and stress measured in what's the unit for force in the SI units? Anyone remember? Yeah. Newton. And then area in SI. Length times width. Meters squared. Newtons per meter squared. That unit in the SI units has a special name. Now this is also stress, okay? Okay? And that name is a Pascal. Now, they'd already used capital P for something else. This was named after Blaise Pascal. They have a little blurb on him on page 316 in the side note. A French mathematician, physicist, and theologian, okay? Interesting combination. And anyway, he did some of the early work with pressure and stress, and they named the unit after him. Newton per unit per square meter. Force per unit area. Now, I want y'all to notice when she opens the door there and closes it. Did y'all notice any change of pressure in the room? I sure didn't. But you know what? A few pascals of pressure happened. When she opened the door, it went down. When she closed it, it went back up. A pascal is a tiny, tiny, tiny unit of measure, okay? Because a Newton's pretty small, but a square meter, goodness gracious, that's the bottom half of that door, you know, is a square meter. So that's a small force over a huge area. That makes for a very small unit. So most of the time we don't measure it in pascals, but we measure it in kilopascals. Now, I don't know if any of you pay much attention to your tire pressure. You do? If you notice, what is that usually measured in? Anyone notice the units, huh? PSI. PSI. In the U.S. customary, your unit for applied force is pounds, and then your denominator is usually square foot. But square inch is also an area, and that's what PSI stands for. Pound per square inch. PSI. And quite often we just call it PSI. Again, that's a pressure unit. Pounds per square inch. Now, pound is a larger measure of force than Newton is. And believe me, a square inch, which is about your two thumb joints together, that's a square inch, is a lot smaller unit than the lower half of that door, which is a square meter. So a PSI is a much bigger unit than a Pascal. A PSI and a kilopascal are closer to being the same thing. So that's why quite often you'll see. And on your tires, if you'll notice, they'll have so many PSI and in parentheses, or maybe the PSIs in parentheses, they'll also have them on kilopascals. They don't ever say pascals. That would be a huge number. So you'll see both of those. So kilopascals or pascals. Pounds per square inch are PSI, and newtons per square meter are pascals, more likely kilopascals. Now again, the force is in Newton in the SI unit, pound in the U.S. customary unit. Your area in SI, almost always square meter, in U.S. customary, quite often square inches, sometimes square feet. Now, are you under any pressure now? You feel any pressure? Actually, you are. You're under 1 atmosphere of pressure. What does that mean? It means the entire atmosphere above us, which goes up for miles and miles and miles, okay? Believe it or not, the air weighs something, okay? And it is indeed putting a force on us. You are under 1 atmosphere of pressure, which is about 14.7, let's just round it to 15, pounds per every square inch of your body. So multiply how many square inches on your body times 15, that's how much force is on you right now. Why don't you feel overwhelmed? Well, because we grew up with it, but secondly, you're pushing out. Your body is pushing out with actually just a little more pressure than that, okay? For instance, if you were to, thank you, cut yourself, which way does the blood go, in or out? Out. That means the pressure inside your body is greater than the pressure outside. So you don't start sucking air in when you cut yourself. The blood comes out, which is a good thing to happen. You don't want to be pulling germs in. You want to be making sure they get flushed out. So you're under quite a bit, 14.7 pounds per square inch right now, okay? And think how many square inches are on your body, okay? Now we're going to consider this illustration. Okay, here we have a brick. And this brick, either one of these bricks, has a weight, of course. Get my pen set up. The force due to weight for both of these bricks, they're identical bricks, is 12.0 newtons, right? Okay, that's what they tell us in the book. Imagine a brick weighing 12.0 newtons, lying on its side, okay? Now, both of these are lying on its side. Which one are they talking about? On the table, and then standing on the end. So the first one is saying lying on its side. I would be say that one's lying on its face, but okay, we'll take the side. Lying on its side, on a table, and then the same brick standing up on the table, okay? Now, the dimensions of both bricks are identical, just like their forces, the weights are. They're 8 centimeters by 16 centimeters. That's the area of the base here. Well, that's 8 times 16 be 48. 128 square centimeters. Okay? That would be the area of the base of that brick. But when you stand it on its end, it's 8 by 6. So this is the area of the base, okay? The area of the, let's call this area of the base, and the area of the end is going to be 6 times 8 is 48.0 square centimeters, okay? Now, the question is, are the pressures the same? The weight's the same, the brick's the same, is the pressure the same? What you think? Yay or nay? Actually, the pressure of the one standing on end is greater than the one lying on its face because it has a smaller area, and remember, pressure or stress is equal to force per unit area. Okay? And the first one is 12.0 newtons. Now, I think I know what they're going to do here. They're going to try to get the pascals. So what we need to do is convert the 128 square centimeters into square meters. Okay? So we got to do a conversion there. So I think I'm going to bring it down here where I have a little more room to write. 128, I think I've got that right. Yep. Where did it go? There it is. 128 square centimeters. I need to make a conversion here to get this to square meters, because that's what we measure pascals in, square meters. All right. You tell me what unit is going to go. Remember, these two blanks, one's for numbers, one's for units. Always put the units in their place first. What unit goes where? One's on top, one's on bottom. Say again? Centimeters over meters. Is that what you said? Centimeters over meters. If I do that, I wind up with centimeters cubed or to the fourth divided by meters to the square. That doesn't give me meters squared, does it? What's that? Yeah, this is a multiplication. You divide them out early. So what I'm going to do, notice, yeah, you put the meters on top because that's where you want them to be, and you put the centimeters on the bottom so they will cancel out. Okay. Now, we're not quite ready to cancel yet because I want the conversion first. How many centimeters in a meter, or how many meters in a centimeter? How many? 100 centimeters in 1 meter. Just think of a penny. A cent, 100 cents, and $1, which is a cent. A penny would be a cent a dollar. Okay, that's why they call it cent. So 100. Now, but we don't have meters and centimeters, do we? We have squared meters and centimeters. So we're going to have to square the units to make them match, but we also have to square the numbers to make them match. Okay? Now, I can tell you what 1 squared is. What is it? 1. Okay, so that's just going to be 1. But 100 squared is going to be 10,000 because you've got to double your number of zeros because you're squaring. So that's 10,000 square centimeters. Now you can cancel your square centimeters out, and what you're doing when you're dividing by 10,000, you're moving the decimal 4 places to the left. So let's move this 1, 2, 3, and 4. We'll have to put an extra 0 in there. So that's 0.0128 square meters. Okay, so that's the area we put here for the stress or the pressure on the base. Divide that by 0.0128 square meters. Someone with a calculator, do that division. 12 divided by 0.0128. Anyone get an answer yet? 937, is that what you said? 0.5? All right, that sounds about right. And what units? Did you say PA? Yeah. Newtons per square meter is the same as a Pascal. Okay? So this would be now. How many significant digits did we have here? 3 here. Here. Okay, here. Whoops, that was a 1. Okay. 3. We got 4 here. We don't have 4, so what would this round to? 938, because the 5 is 5 or more, so you round up. That would be pascals. Okay? Now, okay. It's going wherever it wants to. We got to do the same thing, but this time we need to convert our 48.0 square centimeters to square meters. And we do it the same way. What goes on where? Remind me? Meters on top, centimeters on the bottom. How many meters in a centimeter or centimeters in a meter? Same as before. How many centimeters? Okay, 100 centimeters, 1 meter. But then you have to square because you have square units here. Square, 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 and even square that. That's no importance. This comes out 10,000 again. Okay, which means move your decimal 1, 2, 3, 4. 0.0048. Okay, so I'm running out of room. I think I'll do it up here. Stress on the end is going to be weight, which is the same as before, 12.0 newtons divided by 0.0048. It actually technically has another 0. You don't need it here, but we'll put it down. Square meters, now that we've got it in square meters. This is, I can't write it in there, but this number here goes in there, okay? And someone with a calculator tell me what that comes out to be. 12 divided by 0.0048. 2,500 on the nose. Wow. And that would be newtons per square meter, which is also Pascal. Now, if you don't like that big a number, 2,500 Pascal, what smaller number but bigger unit could you use? 2.50, you always have to have 3 digits, kilopascals, kPa. Now, on this one, you need to put a bar over that first 0, meaning it is significant, because we had 3 digits, right? Yeah. So that's how many Pascal, or 2.50 kilopascal. All right, is that making sense? And sure enough, go home and try it. If you have a brick, put your hand down on a tabletop and put the brick flat on your hand. You'll feel it, but it won't be too bad. Then take that brick and turn it up on the end, and you'll feel a lot more pressure. Same brick, same weight, same force, more pressure because you're over a smaller area. Does that make sense? And they show case 1 and 2 at the top of page 317. And then they have this other example that I've given before in other classes. This book gives it. First book, I remember doing it in a while. I was dancing with my daughter, and she had on sneakers, and I misstepped, and she stepped on my foot. But it wasn't too bad, was it? But then I was dancing with Shane Garland, by the way. This time she's wearing high heels, spiked heels. And I misstepped again, and she stepped on my foot with a spiked heel. Same difference. She weighs the same. You think it felt the same? No way, okay? And it's not because of weight, force, it's because of pressure. Reduce the area, increase the pressure big time. And that's exactly what they show in your text in the next example. And let's see if they have a slide for that. No, they don't. Okay? Now, so let's go to that one. Since I've written all over the screen on that one, let's get out of this one and go back to the other thing and work my darling shoes. Okay. And I got to get my pen back. Okay. Let's say the woman weighs 160 pounds. What's that a measure of? Pounds is a force, and that's the force due to weight, and this is 160 pounds. Now, they don't put a bar over that 0, so I assume that's only 2 significant digits. Okay? And it says, for example, if she rests her weight on a 4 square inch heel. Now, that might be about like my heel here. Just looking at it, it looks like about 4 square inches. Let's just say maybe hers isn't as big as mine. So let's say that's the area, is 4.0 square inches. Okay. What would be the stress if she's resting her full weight on that one heel? What's the stress on the floor or your foot or whatever she's standing on there? What's the formula? F over A, and in this case it's 160 pounds over 4.0 square inches. Okay? That's pretty easy to do, isn't it? That would be 4. 4 going to 16 4 times. Bring down the 0. That 0 is significant. 40, what unit? Second? PSI, pounds per square inch. PSI. You could write pounds per square inch if you wanted to. So that's with her sneakers or whatever. It shows flat heel shoes, okay? Now, this time she puts on her spike heels. Same woman, so the weight is the same. Force due to weight is 160 pounds. That hasn't changed. But now the area on that spike heel, this is on the flat shoe, this is on the spike shoe, and this is going to be 1/4 of a square inch. Now, I hate they put it as 1/4 of a square inch, but it's okay. Okay? Why in the world did that come out? Sometimes that was a 2, but it didn't come out looking like a 2. Okay. 1/4 square inch. Okay, do you want to deal with the fractions or you want to deal with decimals? I don't care really. You tell me. Fractions or decimals? How do you want to work the problem? Fraction? Okay, we'll do it. What's the stress now? Same formula. Force per unit area. Now your force, same as before, 160 pounds, and we'll assume that's 2 significant digits. Okay. Now the one advantage to doing it in decimals, you can see the significant digits. But we'll count it as 2, and that's divided by 1/4 of a square inch. Okay? Now, how do you divide fractions? What I would suggest, since we're doing it with fractions, that'd be 160 pounds, and you can put that over 1 if you want to, let's do divided by 1/4 of a square inch, right? Okay? That's the same thing. That's a long division line. This is a dividing symbol, okay? And how do you divide fractions? 160 pounds over 1. How do you divide fraction? Multiply by the reciprocal, 4 over 1, and now your square inches are down here. It's sort of bizarre to keep up with the units like that, but the square inches are in the numerator, basically. So now they're in the denominator. Okay? Well, what you get here, 160 times 4 is, anyone? 640. That 0 is not significant. What units? What units? PSI, pounds per square inch. Perfect. So, just that change of shoes increased the pressure about 16 times, okay? Because you decrease the area by about 16 times. Pretty major difference. This would have worked out exactly the same if you had put 0.25 square inches. And then your calculation would have been maybe just a little easier. And you see 2 significant digits there. So 640 PSI, pounds per square inch. Okay, we're going to do something fairly similar with SI units. This time we have a 65 kilogram woman. What's that a measure of? Say again? Not quite. Kilogram measures mass, okay? You got an extra step in this one. Okay? In order to get a force, what do you have to do with the mass? The force due to weight. What is that formula? You remember that? A couple chapters ago. Anyone remember? Remember Newton's second law. Mass times acceleration due to gravity. mg. And what's g in the SI units? That would be 65 kilograms times, what's G in SI units? 9.8. Usually they give 9.80 to give you 3 significant digits. We only need 2 here, so we'll just round it to 9.8 meters per second squared. Okay? And that gives us what? Something around 640 some? Anyone do that? 65 times 9.8? Anybody? Huh? 637. 637, and that's what unit? Newton. Kilogram meter per second squared is a Newton. So that's her weight now in newtons, and she rests her weight on a 25 square centimeter heel. I think that's more like a 4 square inch heel. So, stress formula, same as before, force per unit area. But now the force is 637 newtons divided by, what do we say, 25? Oops, here we go again. The 25 square centimeters. Remember what we did to get that to square meters? We don't have to go through it again if you can remember. Move it 4 places to the left. Divide by 10,000. So that's divided by 0.0025 meters. Now it's meters squared. Someone punch that into your calculator. 637 divided by 0.0025. Anybody? Let's say about 254,000. Is that what you said?
Yes,
And what? How many hundred?
800.
800. Okay, that's important. So let me get back. 800. Okay. 254,800. What units? Pascal. That's a mighty big number, so I think I do want to make it a smaller number and a bigger unit. What would that be? 250. And since we only need 3 significant digits, do we? Or do we need just 2? I think we only need 2 significant digits. So that would round to 250 kilopascals. Because you only need 2 digits. Remember, you had 2 digits here. We used just 2 digits there. This was 2 digits, everywhere 2 digits. So we round the 4. It's less than 5, so we drop it, put a 0 in its place. 250 kilopascal. Now, if that is equivalent to 40 psi, which I think it was, you see that still it's a lot bigger number, but 250,000 Pascal, nowhere close to a Pascal. That's so there's still a PSI is even bigger than a kilopascal, if these are equivalent, and I think they are. And they put 250 kilopascal. Okay? But what if she goes to a spike heel that has 1.0 square centimeters? So the area for the spike heel, 1.0 square centimeters. Okay? Now you know what we're going to have to do. Change that to square meters, and how many would that be? Remember what we did? Move your decimal 4 places to the left. 1, 2, 3, 4. 0, 0, 0, 1. So that's 0.0001 square meter. Okay? Now we'll use same formula, only this is for the spike heel. I don't know why I put P. Spike. Oh, that's ugly. Okay. The spike heel. Same force. Don't have to calculate that again. 637 newtons. This time we're dividing by 0.0001 meters squared. Now, I can do that without a calculator. Yeah. This computer is just going nuts today. Okay? Let's just move this decimal 4 places to the right and move this 4 places to the right. And that would be 6,370,000 Pascal. But we only need 2 significant digits, so that would be what? 6. How would you round that? Help me, somebody. 6,400,000 6,000 pascals. Or if you wanted a smaller unit, smaller number but bigger unit, that would be what? Help me. 6,400 kilopascals. My pen is really slow. So if that's still too big a number for you, you could actually say that is 6.4 megapascals. Now, most of the time we don't use megapascals, but you could. That's the next metric unit up. Okay? Let's see what they got. They said 6,400 kilopascals, just like we did. And again, you increase the stress by however many times that is. Quite a few times. From 250 kilopascal to 6,400 kilopascals. That's a huge amount of stress or pressure. Okay? Now, the next two characteristics or features of solids, properties of solids. So it's all right for me to erase this slide? Yay or nay? Okay? All right. Is tension. These all sounds like words that apply to us today, wouldn't it? No, tension. What tension is a stress caused by two forces acting directly opposite each other. Okay? Now, that doesn't quite define it. These two forces could be acting opposite each other, but so could these. They're still acting opposite each other. This is the stress, when they're acting away from each other, pulling the object, in other words, trying to lengthen it and make it narrower. That is a tension. On the other hand, if they were going this way, still opposite each other, that's called a compression. Okay? That's a stress caused by, so this should be acting directly, I'm going to throw in the word away from each other. They didn't put that in the text, from each other, and the compression is a stress caused by two forces acting directly opposite toward each other. So that's a compression, that's a tension. Okay? The illustration they give in the book here is two teams playing tug-of-war. Okay? They're acting opposite each other. Okay? That's a tension. They put tension on the rope. The next example, and all right for me to erase this one? No, get it. Let you finish writing. Okay. All right, everybody got it? Okay. Would be, so slow having to do this every time. Well, it didn't work. Oh wait, that's not what I wanted. That's what I wanted. Helps if I hit the right buttons. Okay. This would be a compression. Okay. Here, your piling is standing up here, and the cars running over the bridge, and just the bridge itself is pushing down like this. That's a compression. These posts tend to be pressed together. Okay. If the concrete's not strong enough, it could break, shatter, or something like that. My guess is probably steel reinforced concrete, so hopefully that will stand for many years, decades, maybe centuries. Okay. But again, forces per unit area. You measure these in stress units, whether tensile stress, compression stresses. There's one other, and I've already erased the other one. Let's see. Oh, this is the example of compressive stresses. Compressive stresses, okay? This is a column under the New Clark Bridge crossing the Mississippi River. I don't know where that is. I don't think it's New Orleans, but it could be. I just don't recognize that name. Okay? But there is another type of a stress. A tensile stress is when they're going away from each other. A compressional stress is when they're going toward each other. This is another kind of stress. Okay? Someone is pushing on the book, and they're pushing in a, let me go on and give you the name. This is called a shearing. Okay? Let's see if I can find a good place to write the definition so you can have it on this page. Shearing. Okay? A stress caused by two forces applied in parallel opposite directions. I'm going to abbreviate parallel by drawing two parallel lines. Parallel opposite directions. Now these are neither directly toward or directly away from each other. These are offset. Okay? This is what makes it a shearing force. You apply the force. Now, you might say, wait a minute, I can see he's applying a force in this direction. Where does this arrow come from? Anyone want to make a guess? What kind of force always opposes motion? A couple chapters ago. Frictional force, exactly. The friction of the book on the table or the catalog, whatever that is on the table, that is the frictional force. It's pushing this way, opposing the motion. He's pushing this way. They're parallel, opposite directions, but offset. Okay? That's what makes it a shearing force. Okay? Now you can have shearing forces in many ways. The next diagram shows the shear, you might say. Here, one force is in this direction. On the book, that was the frictional force. The other force was that way, pushing the top, but they're offset, so that creates a shearing. I grew up on a farm in Georgia. One of the summer jobs we often had was baling hay. And always a hay baler, because that was a big, expensive piece of equipment, it had a big wheel. The power takeoff from the tractor turned like this, and it turned the mechanism in the baler, and it packed the bales, it picked up the hay from the ground, shoved it back. You know, it was really complicated, pretty complicated piece of equipment and wham them together and then tie it. Okay, it's a real nice piece of equipment, all together, fine. But if you picked up a rock or a stick or just something jammed in there, you didn't want to tear up your whole tractor and your whole baler. This big flywheel that you had here had two pieces, and in between was one bolt. Maybe a few others, but one bolt that if it got jammed, it would shear, because one force in one way and one force in the other, rather than tearing up your equipment. So that was your safety. If it got jammed, the bolt would shear, you wouldn't tear up the whole piece of equipment. Easy to replace the bolt once you got the obstacle out of the way. Not so easy to repair a whole new baler. Okay, so this is a shearing force, two different directions, opposite each other but offset. Okay, that's the shearing force. Now, there is another sort of kind of shearing force that is a torsion. Okay? Now that sounds like tension, but it's not quite the same. It's a stress in a twisting motion. Now, in reality, this is really also a shear, okay? Because the wrench here is being pulled this way, okay? So it's twisting this way. The friction down here, as you're trying to twist this bolt into place, the friction down here is resisting the motion in that direction. That's also a type of a shear. That's a twisting shear, and that's called a torsion. You can almost see the word in here, torque. Torque is a twisting motion, and so this is a twisting shear. Twisting force. Now, do they have enough of these or what? Oh, and here's the torque. And the symbol for this is the Greek letter tau. That looks sort of like a T, but it's the Greek letter tau. T-A-U. Corresponds to our T, but they usually use the Greek. That's given for torque or torsion. Okay? You're twisting the bolt one way, and the resistance is tending to keep it in place the other way. Now, I don't know if you've ever, say, turning a bolt or a screw or something like that, you've actually had one snap. I have, okay? And that's when the strength of the material isn't strong enough for that torsion to happen. I've also had, when it's a screwdriver, the head of the screwdriver just tear up the slot, okay, and wear it out so you couldn't turn it anymore. That would be because the torsion was too great. Okay. And then there's this one. This is simply a bending motion. And a bending consists of both a tension and compression. Going back to tension, not torsion. I can't write. T-E-N-S-I-O-N, and compression. Okay, now how is that? Well, notice the guy sitting on the board here. I'm guessing he's one of the authors, but maybe he's a grad student or something. The lower part of that board is being stretched, but the upper part is being tensed. All right, I did it backwards. Compressed is like this, stretched or tensioned on the bottom side, compressed on the upper side. Okay, and a bending is a combination of those two. Not too careful, that one may actually break, okay? And this was sort of the example I was giving on an earlier example, okay? So here is the compressive force, here is the tensional force. The upper side is compressed together, the lower side is tense apart, and if the board's not strong enough, it'll actually break, give way, okay? Obviously it's bending, but if it passes its limit, then it actually breaks. And here is, I guess this is a piece of of foam rubber or something, and they're showing here, if you press it right, you force these together, that's your compressional forces, and spread these apart, that's your tensional forces. Okay. Same thing with the big gradations there. We finally hit example 1. Okay. So let's go back to this slide, current slide. Get my pen back. Okay, example 1. A steel column in a building has a cross-sectional area of 2,500 square centimeters. So the area of this steel column, I'll put steel column, is equal to 2,500, and the first zero is significant, square centimeters. Okay? And supports a weight of F sub W, the weight, is 1.50 times 10 to the 5th newtons. Now, time out a moment here. Seems like we have done some scientific notation before, but do y'all know how to operate with scientific notation? Know how to use your calculators to do that? If not, I'll sort of try to talk you through it. So get them out, get them ready, because you're going to see problems like this that you probably want to use scientific notation. So get ready for this. Supports a weight of 1.50 times 10 to the 5th newtons. Find the stress on the column. So we're looking for stress. What's the formula for stress? Yeah, force divided by area. And they gave us this. What's the only problem with this problem? Okay? Your units. What units do you want that to be? Newtons are fine, but you want that to be meters squared. And we've done that conversion several times. You remember how to do it? Yeah, move the decimal to the left 4 places. 1, 2, 3, and 4. All right? So this will be 1.50 times 10 to the 5th newtons divided by 0.25. I'm going to put the 0 there just because it's significant. You don't need to in your calculations, but I'll put it there just to remind you. And this will be square meters now. Okay? Now, for those of you with calculators, do any of you not quite sure how you do scientific notation? Anyone? Or all of you got it down? Okay. Let me say this. You type in the 1, or you press the buttons for 1.5. You don't need to put the 0 if you don't want to. Do not do a times 10. Okay? That's not the way to do scientific notation. What you do for this is 1.5. I'm going to leave off the 0 for now. Then look for a key. And this key on some calculator is EXP. Other calculators will be EE. One of those two keys. And if you can't find either one of those, there may be one that's a caret key, but I think most of the time it's going to be one of those two keys. And then as soon as you type that key, you'll see a little box come up. You'll see the 1.5 in sort of big numbers, and a little box comes up, and that's where you type in 5 for your exponent. Okay? Then you do divide, and you don't need to put the 0. I'm going to write it just because it makes it easier to read. 2, 5. You don't need that extra 0 either, and then press equal, and you get an answer. Anyone got it? 600,000? And what units? Pascals, newtons per square meter. Okay? That's an awfully big number, so how could you also write that? Smaller number, bigger unit? Help me, somebody. 600 kilopascal. Now, on both of those, we really need to indicate which our significant 0 is. It's not the first one, it's the second one. In both cases, okay? If you write it 600,000 pascals, count 3 digits, put the bar over that third digit that's a 0. If it's kilopascal, same thing. Count 3 digits, put it over that third one. 600 kilopascals. And that's what they got. Now, if you wrote this in scientific notation, which maybe your calculator did, that could have come out 6.0, except it could have just said 6. And some calculators will say the EXP, or just E, 5. Okay? Because you're 1, 2, 3, 4, 5 digits. Okay? So if you see an answer like that, that means 6 times 10 to the 5th. Move your decimal 5 places, you get 600,000. Okay? Kilo, or that would be pascals, or 600 kilopascals. All right. The next issue that we're going to take on is elastic behavior. And I know we've talked about this some before, and this follows Hooke's law. There was a pretty famous British chemist and physicist in England. He formulated the law governing elasticity, and this is often called Hooke's law. He invented the balance spring for watches. He worked with and made important observations with a telescope and microscope. Did a lot of activity. Really a famous, very good scientist, both chemist and physicist. The trouble is, and it wasn't really a big trouble, but it sort of was a little bit of a trouble. He was a honcho, probably one of the honchos in the British, they called it the, oh my goodness, Royal Society, okay, of scientists. When along came this young upstart named Isaac Newton. And whereas this guy had been sort of top of the heap, along came Newton, and everybody else started looking smaller, okay, because Newton just ran circles around everybody. And he didn't particularly get along too well with Hooke, even though Hooke was very well established, very senior guy. Newton he wasn't a very easy person to get along with. And they had some issues. But anyway, here's Hooke's law. The ratio of the force applied to an object to its change in length. Okay, there's a lot of 2's in there, so let me clear my screen here. Is that okay? Everybody got it? Okay. Here's Hooke's law. The ratio of the force applied to an object okay, that's one phrase. The force applied to an object. Think of that as your numerator. Okay? See, a ratio always compares two things. This is the force applied to an object to, now this is the important to here, the ratio from this to that. This is just applied to an object, just a regular old preposition there. To its change in length, and I wouldn't actually, yeah, I guess so. Change in length, okay? Now, this change of length could be one of two ways. And basically, think of a spring, okay? Think of a spring. You can pull the spring this way and increase its length, or you can push it this way and decrease its length, okay? So the ratio of the force that you exert when you pull to the change of length, that's what the Hooke's law is governing. Or the force with which you push this way and change the length that way. So that can be either being stressed or compressed. That means, I'm sorry, I've been talking about stressing so much, I'm stressing out over it. Stretched or compressed. Okay, I'm writing stressed in my sleep here. Stretched or compressed. Okay, whichever. It works the same way. By the applied force, I won't put that in, is constant as long as the elastic limit has not been exceeded. Okay. Now, here's what that means. The ratio, meaning comparison in the division sense, division, catch that, of the force, now we'll call this the applied force, the ratio of that to the change, delta means change in length. This is a constant, and they usually call that constant K, okay? I think that's from the German word constant, but that's what it usually is. Now, that's one expression of Hooke's law, as long as you don't exceed the elastic limit. Now, remember that spring? Remember, I'm thinking of the one that used to come in the ballpoint pens. Remember that spring? Maybe you took them apart and played with it some. If you played with it too long, you probably stretched it too much, and it was no good anymore. Okay, then you had to buy a new pen. Okay. So, as long as you don't exceed that elastic limit, the ratio of the force that you apply to the change of the length is going to be constant. Pull a little bit, it stretches a little bit. Pull a little bit more, stretches a little bit more. Compress a little bit, it changes length a little bit. Compress a little bit harder, compresses a little bit more. That ratio is always constant, okay? As long as you don't exceed the elastic limit. And this is often called the elastic constant, often called Hooke's constant. I'm surprised this book doesn't call that. Okay, after Hooke's law. The delta means difference, change in. Okay? Now, All right to erase? Are y'all still writing? Okay. All right. Need to discharge this and get back to this one because here is the example. Here's how. To me, this is always backwards. I always think of the independent variable as going on the horizontal axis and the dependent variable going on vertical. Here's the independent. This is the action you take. This is the result. You change the length. So they got them backwards, but I guess there's a reason so you don't have vertical slopes or something. So anyway, as long as you're in Hooke's law range, you put a little bit of force, you get a little bit of change. Put more force, you get more change. More force, you get more change. Okay? As long as this is a straight line or pretty close to a straight line. Here it's very straight. Here you're beginning to deviate a little bit. I would have taken this dot and brought it back to here maybe there. Okay? That would be Hooke's law range. Anything beyond that, then you get in what they call the plastic region where you deform it. That spring doesn't come back. You stretch it too far, and now you got a crooked wire, okay? Not a spring anymore. That would be when you reach the plastic region. Now, if you kept adding a force this way, and that's why it looks like these ought to be swapped. Kept adding a force, at some point you actually break the wire, okay? That's called fracture. Some materials will follow Hooke's law to a certain point and then fracture before they go to plastic, okay? Glass will do that. If I were to, I'm not going to, but if I were to push on that glass, it's probably not going to give much, but it would give just a little bit. Push a little harder, it gives just a little bit more. And I always come back to its original shape, the elasticity. Until I press just a little too hard, and then it fractures. It actually fractures. Okay? So, some materials won't go into plastic region, they go straight to fracture. Okay? Now, I wish I had done this earlier. Remember that formula I gave? I wrote it the way the book did. I can't get my pen to come back. There we go. The applied force to the change of length is equal to a constant. Okay? Quite often you'll see Hooke's law done this way. The applied force is equal to a constant times the change of length. That's how I see it more frequently. All you do is multiply both sides by the delta L. But according to the statement, the ratio of those two is constant. That would be the better definition. In practice, we often use the horizontal, not the vertical one. Okay, so let's move to example 2. Okay, let's see if they have this. No, they don't. Okay, I'm going to go back a few slides if you don't mind. This one right here, or the next one. This is an example. You put a weight on the bridge, just the weight of the bridge, and then all the cars on top of it. You're going to compress that piling by some small amount, okay? It will expand later when you take some of the weight off of it. But that is an example of Hooke's law. You don't want it to reach a plastic limit or fracture limit, okay? No, you don't, okay? So, let's go back to our other slide. Goodness, I get tired of doing this. These slides are so terrible. Okay. A force of 5.00 newtons is applied to a spring. So here's the picture here. Let me get my pen set up again. Okay. Here's the picture. You have a spring hanging here. Okay? Now, what you do you put a weight of 5 newtons on that spring. Okay, I'm not going to do it yet. I'm going to do it here. When you put it on, then it stretches that spring and it goes down here. So here is your 5.00 newtons. This is your weight, F sub W, your force. Okay? A force of 5.0 newtons is applied to a spring whose elastic constant, what was that elastic constant called? Constant, German, K. The K, simple word. K is 0.250 Newton per centimeter. Okay? Now, time out for a moment here. Up until now, we've just about been using exclusively metric units. I'm sorry, SI units. Okay? When you get to this one, don't change that to meters, because meters going to measure such a tiny number, it's not going to make sense. I mean, it makes sense, but it's just going to be a pain in the neck or some other body part. Okay, so let's leave it in centimeters. The constant is 0.25 newtons per centimeter. Okay, that's the elastic constant. Find the change in length. So what we're looking for here is your delta L. Okay, how do we do that? Okay, all right. Is it Addison? No. Lydia. Okay, Lydia. All right, good deal. Okay. Now, before you leave, let's make sure you have both the tests. Okay. All right. So here is what you're, wrong pen. Here is what you're looking for. Now, what formula relates force or weight, spring constant or Newton's constant or elasticity constant, I mean not Newton's, Hooke's constant, to change of length? What relates those? What formula is that? Just had it written up a couple of different ways. Any way you want to write it. Anyone remember the formula? Important to get these right. Okay, say that a little louder or slower. Okay, F sub A over change of length equals your K. All right, that's one good way to express it. What we are trying to get is the change of length. The big boo hiss here is that that's in your denominator, which is about the least convenient place for it. So how can we move that to a numerator and isolate that by itself? What is your inclination here? Multiply the delta L by both sides. Good deal, thank you. By both sides of the equation, and here they'll cancel out, and what you have here, I'm going to rearrange the order, K times delta L is equal to F. And by the way, this is just like those that we did with the triangles and circles. You can express them 3 different ways here. But we still don't have it where we want. We want delta L by itself. So how do we divide both sides by K? Perfect. Okay? So then we have delta L is equal to force, which was 5.00 newtons, divided by K, which is 0.250 Newton per centimeter. Okay? Now, There's a couple ways you can do this without using the calculator because I don't have one. I'm going to do it this way. I'm going to move this decimal 2 places here, that decimal 2 places. Same thing, I'll just multiply the numerator and denominator by 100, which is perfectly fine. 25 will go into 500 how many times? 25 will go into 100 4 times. 500 would be 20 times. 4 times 5 is 20. So this would be 20. No. Yeah. 20.0. Oh, what units? Here the newtons cancel out, and you're left with 1 over centimeter. What does that turn out being? When you're dividing fractional forms, that's the same as 1 divided by 1 over centimeter. Right, that's the dividing line. And then flip this 1 times centimeter over 1, which is just simply centimeters. So you have stretched this spring 20 centimeters, 20.0 centimeters. Does everybody see how that works? Now you can do it on your calculator. You don't have to move decimals. I was just doing it because I didn't have a calculator. Did you get that on your calculators? Okay. And you put a 0.0 because there's 3 significant digits everywhere. All right? Any questions on that? Okay. Example 3, top of page 322. Okay. I'm going to erase some stuff here, but not all of it. We may need some of that back, but we'll retrieve it if we need it. Might have been quicker just to erase the whole slide and write it all back again, but I'm lazy. Okay. Example 3, top of page 322. A force of 3 pounds stretches a spring 12 inches. So this is going to be 3.00 pounds. And that's also going to be our weight. And now they're telling us the delta L here is going to be stretched 12.0 inches. Okay? 3 pounds stretch the spring 12.0 inches. What force is required to stretch it 15 inches? So we're going to do another same spring, but this time we want to know how much weight or force will stretch it from its original to here 15.0 inches. So this is delta L2, okay? This is delta L1. And this is force due to weight 2. This is force due to weight 1. Okay? Okay. How might we do this? Or maybe a better question is, what formula might we use? Okay, I think I heard it. FW or FA or whatever over delta L is equal to K. Okay, all right. Our first part of the problem, this fits like a glove. What this tells us is K for the spring. This information will give us K. And we don't know K, so it's a nice thing to know. So let's plug it in and see what we get. What is our applied force? 3.00 pounds. And how much does that stretch the spring? 12 inches. Okay, so it looks like our K is going to come up in pounds per inch, which is okay, perfectly fine. And what will that be? I can't. I don't know where my brain is tonight. Whoops. Don't you get 0.25? Or do you? Anybody? Yeah. Pounds per square, pound per inch. I'm so used to square inches now. Okay. Pounds per inch. Now we know the K. Now we can answer the second question. What weight is going to stretch that same spring constant, remember it's always good, by 15 inches. So now we just change our formula, and now we're looking for the second weight. So what would that be? How do we change this formula? F sub A, we'll call it A2, over delta L given K. Same spring, so same spring constant. How do we get F sub A2? Isolate this. Multiply both sides by delta L. Perfect. These go out, and you get F sub A2 is equal to K times delta L. Remember I said that's the way I'm used to seeing Hooke's law written, which is the K is 0.250 pounds per inch. Multiply that by what is our new delta L? 15.0 inches. Punch that on your calculator and see what you get. Yeah. Second? 3.75 what unit? Pounds, because your inches cancel out. Inches are your units are your friend here, so this will be pound. And let's see, we had 3 significant digits there, 3 significant digits there. We're in good shape, so we'll use 3.75 pounds. That's how much it would take to stretch it, that extra 3 inches. All right, good deal. All right, ready for example 4, bottom of page 322. All right, to erase? Everybody got it? Okay. A support column is compressed, whoa, and by the way, 3.46 times 10 to the minus 4 meters, okay? Under a weight of 6.42 times 10 to the 5th, big numbers here, newtons. Of course, that's in newtons. How much is a column compressed when under a weight of 5.80? 5.80 times 10 to the 6. Okay. Now, what would be your approach to this problem? What does that first set of information, that first sentence you might say, what does that lead you to be able to conclude. Very much like the last problem. Yes, that enables you to calculate the K, because we don't know what K is. We know and what is this, 3.46 times 10 to the minus 4? Hint is measured in a length unit, so that's, it's compressed that much. That's a, help me somebody. Change of length, delta L. And what's his weight? What would that be? Weight is a the units help give it away. What you would measure in newtons. Force is. This is our force. This one happens to be due to weight, or the applied force when you put it under that much weight. Okay? Think we can use that to get a K? What's the formula? FA or FW, either one, over delta L equal K. And what's your force? 6.42 times 10 to the 5th newtons divided by the delta L, 3.46 times 10 to the negative 4 meters. All right, they're really piling on the scientific notation here. Okay, my eyes are burning like crazy. Y'all remember how to enter scientific notation? Okay, 6.42, and then find the key, EE or EXP. Some calculators are one, some are another. If you don't have either one of those, I'll try to help you find something to use instead. And then all you type in after that EE or EXP is 5. Do not type in times 10. It's 6.42 EE or EXP 5. Okay, everybody got that? Divided by 3.46. Again, don't type in times 10, EE or EXP, but this time you do a negative 4. Now this may be a problem for you as well. Okay? So I'm going to write this out, how you do it. 6.42, and again, it's either EE or EXP, one or the other, okay? 5, that's your exponent, divided by, that's your division line here, 3.46, again, your EE, or, I'm sorry, don't need a line there, or EXP, whichever your calculator uses. If it doesn't use either one, let me see and I'll try to find it. Now you do a negative 4. Now on your calculator, there are 2 negative signs. One's over there with the plus, minus, multiply, and divide. Don't use that one. Look for one that is in parentheses, a minus sign. Do you see that? Use that negative sign and then do your 4 and then do your equal. Okay? See if you get an answer. It should be a pretty large answer. Anyone see it? Get it? Okay, what is it? Okay, just read off the digits to me.
18.
Say again? Isn't it 186? Does it start that way? Okay, okay, that's fine. Read them off to me. 185. Another 5. Keep going.
49.
4, 9.
13.
1, 3.
29.
2, 9. Okay, and that's ends, right? That got it?
Yeah.
Okay. Way more digits than we need, right? So here's what you do. Start blocking them off in 3s. Okay. And that would be, okay, I'm going to go back to scientific notation. Some calculators will give you that automatically. This one obviously didn't. So this would be 1.8. Now we only have 3 significant digits, right? 3 here, 3 here. So count 1, 2, 3. Look to the right. What do you see? A 5. That's 5 or more, so you bump this up to a 6. 1.86 times 10 to the, how many places you go? That's 3, 6, 9. 10 to the 9th. And your unit is Newton per meter. Newton per meter. Okay? That is your K. The spring constant. Only it's not a spring now, it's a compression constant. Okay? Elastic constant, Hooke's constant, whatever you want to call it. There's your thing. Now, I wouldn't erase my screen though. If you got that 1, 8, 5, 5, 4, 9, 1, 3, 2, 9, leave it on there. Okay? Because what's the next part of the problem? That just gave you your K up here. The question now is how much compression when under a weight of this. Well, what is this weight going to be? What will that be? This is forced you to weight 1. This is forced you to weight 2. This is again a weight. So what are we looking for with how much compression? What's the question we're asking? What's going to answer that? How much is it changed in length? What do we call that? Delta L. That's the unknown here. Okay? So what we want to do is take this equation and solve it for delta L. Now we did that before, but we can do it again. How do we do that? I'll write it down again. F sub W, this time it will be W2 over delta L is equal to K. Same K as we have there. So what will we do? Multiply both sides by delta L. And here the delta L's will go away. And now we want to isolate the delta L, so we're going to divide by K. Okay, I'd hope to be able to use it better, but let's not. Let's go on and round it off. Okay, so this time we'll do our weight 2. Okay, and when divided by this, it disappears. Okay, so we'll do F sub W2. That's 5.8. You can put the 0 if you want to. Remember, how do we do scientific notation? What key? EE or EXP. And then, in this case, it's 6 divided by, and now we're going to have to put in the number we just had, 1.86 EE or EXP 9. And then press equal. See what we get. You expect it to be a larger number or a smaller number than that. You put more weight on it, so you expect a greater delta L. More compression. Not a lot greater, but some greater. What do you get? You can put this as a 80 if you wanted to. What do you get when you divide those numbers? Help me, somebody.
I got decimal.
Okay.
0.003.
0.003. Give me some more digits.
118.
11828. Okay. Now, since everything else has been in scientific notation, including your delta L up here, I would put this in scientific notation. So take your decimal and move it behind the first non-zero number. That would be 1, 2, 3. Okay? So I would write 3.1. Now that's the third digit. That's the important digit. Look to the right, and what do you see? An 8. So that means you bump this one up to a 2. Okay? Times 10, you're going in the reverse direction now. Since you moved this to the left, this is a small number here, 0.003 is a small number. This is going to be a negative exponent, and it's going to be -3 meters. Okay? Because this was 3.46 to the -4. This is 3.12 to the -3. And if you'll notice here, this is just about 1 order of magnitude different, because this was 6.42 to the positive 5. This is 5.80 to the positive 6. It's almost an order of magnitude. This is almost an order of magnitude. 10 to the -4, 10 to the -3. Now, of course, you could write that, because this is an awfully small number, and this, by the way, was meters. How could you make a bigger number smaller unit? What's 10 to the -3 meters? 10 to the -3 is milli. This would be 3.12 millimeters. Okay? Just to give you an idea of what we're talking about there, I happen to have only 2 dimes on me, but I have a penny. Okay? A couple pennies, 3, 4. Okay? A dime is about 1 millimeter. A penny's a little bit more. So we're just going to say those 3 together, that's the amount of compression. A little bit more than 3 millimeters. That would be just about it. It's going to compress. Of course, you're talking about a huge number of newtons. That's 1.9 or 1.86 million newtons. That's it. No, billion newtons. Okay, that's a lot of force. Okay, and it's going to compress that, whatever it was, I've forgotten what it was, support column by 3 millimeters, a little bit more than 3 millimeters. Okay. Let's see what they got. 3.12 times 10 to the -3 meters, or 3.12 millimeters. All right. There's a little physics connection at the bottom of page 323 on development of materials. Pretty interesting read. So if you got your book, that is a pretty interesting read that you have there. Now, all right, to erase this, okay, I'm going back to this slide. Here is a bridge, okay? This was a bridge that was built in 1779 in Colesbrookdale, England. Obviously, they must have done some coal mining there, somewhere around. And a couple things to note there. Notice the bridge sort of has, I don't know, I can't tell for sure. It looks like it's sort of peaking here. And the reason is that when you get a lot of heavy traffic in it, it allows it to settle some. So that's where some of the delta L will happen as it flattens out. I don't know if you've noticed trailer trucks, you know, big rigs that have the flatbeds on them. When they're empty, you'll see there's a little mound in it. When you put a load on it, that mound settles down and gets almost flat. Could actually sink down. They don't want it to sink down. That's your delta L. The amount that is deviating. That's your delta L. That's what we're measuring here. And this is a cast iron bridge, which was fairly unusual because cast iron is usually pretty brittle, but they used it here. Now they also show here what we do nowadays. They pre-stress concrete. And what they do, they stretch as much as they can the steel reinforcing rods in there. Then they pour the concrete and let it settle. And when concrete settles and hardens, it usually has a little bit of gaps in it just because it's evaporating water, okay? That's what the curing of concrete is. And then once it's settled, is cured, then they release the tension on that and it pulls the beams slightly, just a little bit closer together, and they call that pre-stressed concrete. It requires a tension on the cables when the concrete dries, while the concrete is drying, and after it dries, the tension's released, placing the concrete in compression, and that strengthens the concrete. And most bridges now have pre-stressed concrete. Now, they may do this back at the shop, you might say, before they send these pieces out to put them together, or they may do it on site. I don't know which way they do, but I do know Malfunction Junction took well over a year for them to get those bridges done. Hopefully they did them well. All right, that finished 12.2, finally. Homework exercises here would be, and this is on pages 324 and 325, any of the odds 1 through 9 that you can find at the back of the book, and then any of the odds 11 through 19 that you can find in the back of the book. All right? And then next time, because I think we're just about out of time, we will be beginning with properties of liquids. So all this has been properties of solids, but we're now moving to properties of liquid. Some of these are similar. Some of them are quite different, but we'll be dealing with that. Any questions? All right. Good deal. I will shut down the recording.